Good morning, everyone. So if you just send me text in the chat, say hi or good morning, I'll trace that data for the attendance, okay? So we'll get started. Let me share you my screens here. All right, so we'll still be checking on the rest of chapter 23 today, and then I think we are going to check 24 as well, okay? I'm pretty ambitious today, hoping to finish chapter 23 and 24 in the same time, in the same lecture. All right, so let's see, a few reminders items here again. So for this week, we are doing lab week, we are doing lab number 8. Kind of hear some background noise here. Okay, I'm gonna mute you guys all, okay? For right now, but if you want to talk, unmute yourself and you can talk. All right, so this week we are doing lab 8. So you guys on Wednesday you did that, and so for the rest of you guys we will be doing this lab this Friday, this afternoon, okay? Number 9 homework is due on Monday. All right, so you probably want to spend some time during the weekend to do number 9 if you haven't done so, okay? And then we'll have exam 3 on Wednesday, okay? So the next few days, you probably want to spend some time on studying for the exam, okay? Again, we will not have lab next week as we will have Friday off next week, okay? All right. So last time we checked the elements in an AC circuit, okay? So we check on the resistors and inductors and capacitors in the AC circuit, okay? So for a resistor, it just behave as the same as it's in a DC circuit, okay? So voltage and current, if you do voltage divided by current, that will give you resistance, or according to Ohm's law, voltage should be equal to current times resistance, okay? So in this case, the voltage, if we are in an AC circuit, then a voltage is going to be either a sine function or cosine function. Then current should be also a sine function or cosine function, okay? So then the voltage and current on the resistor, they kind of behave similarly to each other. They will peak at the same time, they have minimum at the same time, and the zeros at the same time, okay? So we call them in phase. And for the average power on the resistor, so then because we are having an AC circuit, if we just look at the voltage or current, then it's going to be average is going to be 0. So we need to use the rule mean square quantity to describe it, okay? And then it turns out mathematically the average power is equal to I square RMS, okay? So the rule mean square current square times R, okay? Just similar as what we have been doing for the DC circuit, we'll just use I square times R. In that case, I is not changing, V is not changing, okay? But in this case, because I and V are changing, so we need to use the rule mean square quantity, okay? And then you can also use the V square over R, but again, you'll be using rule mean square quantity for the V. You can also use V times I, then we'll also be using the rule mean quantity, rule mean square quantity of V and I, okay? And then if we have an inductor that is in a AC power circuit, then in this case, the current and voltage, they don't peak at the same time, so they are out of phase, okay? And then the voltage actually leads the current. That means the voltage peaks earlier than the current by 1/4 of a cycle, or 90 degrees, or pi over 2 in radians, okay? So in that case, so you can see the reactions of the inductors to the voltages applied, okay? It's not exactly equals to like if you would use V over R, because in this case we are using an inductor, so there's really no R here, but we can come up with a quantity called reactance of the inductors. Okay, then in that sense we can express similar to the Ohm's law. I is going to be equal to V over the reactance. Okay, reactance is represented by the symbol X. In the case if you have an inductor, then you use XL. Okay, for inductors, XL is equal to 2 pi times frequency times L. Okay, so proportional to frequency and also proportional to the inductance. Or you can write it in terms as XL is equal to omega times L. Okay, so omega is the angular frequency, which is 2 pi times F. All right. For the voltage on the inductor is it's going to be a sine function, and then current you can write it also as a sine function, but with a phase change. Okay, so the sign is not the same, but there's a phase change difference of pi over 2 or 90 degree. Okay, but this case you can write this as a cosine function. Okay, so it's going to be cosine of omega t then. So now if we look at the average power, we are going to use V times I on the inductor, and then we checked this last time. It turns out that the average power on the inductor is going to be 0. Okay, so that indicates the inductor doesn't consume any power, which is a good thing. Okay. Also for the capacitors, if you place them in a AC circuit, then in this case, again, the current and voltage, they don't peak at the same time. They're out of phase by 90 degrees, okay? But in this case, the current leads by 90 degrees, okay? So then current and voltage can be expressed in different sine functions, okay? Or you can write, again, current as a cosine function. For the current going through the capacitor, then we'll be using the reactance of the capacitor, so we call it capacitive reactance. In this case, X sub C, C denotes capacitor, equals to 1 over, okay, now it's inverse of 2 pi F times C compared to for an inductor, so different expression here, okay. And if we look at the average power, again, in this case, for a capacitor, it turns out to be equal to 0. So that means, again, capacitor doesn't consume any power in the circuit. Okay, so capacitor and then inductor, they both, either of them consume any power. So when they are present in an AC circuit, they simply store energy. Okay, and then later on, they will release energy. Only the resistor will consume the energy in the AC circuit. Okay. All right, and then we look at the scenario of we a combination of all this together, all these 3 elements together in an AC circuit. Okay, so then we will be using a term called Z, called impedance Z, represented by symbol Z, as the reaction of the combination of elements to the AC source. Okay. Z impedance, similarly to resistance, has the same dimension as resistance, is equal to square root of R squared plus XL minus XC squared. Okay, so reactance from inductors, the differences of the reactance from the inductor minus the reactance from the capacitors. Okay. All right. Then use the Z, we can calculate the root mean square current of the circuit as a whole. Okay, so now in this equation you can see, so I can be calculated in terms of V over the Z, the reactance. Okay, now XL is equal to 2 pi FL. Okay, XC is equal to 1 over 2 pi F times C. Okay, so then in this case, you can see R is constant, XL is a function of frequency, XC is also a function of frequency. Okay, so these two are changing. So there's a scenario which, because this is proportional to frequency, this is inversely proportional to frequency. Okay, so then you can actually tune the frequency, so you can make this two XL equal to XC. Okay, that's possible. So simply you just set up the 2 pi FL equals to 1 over 2 pi FC. All right. So then given L and C, you can figure out what's your frequency that needed to make this term vanish, okay? So that means XL minus XC goes to 0, all right? So if that happens, then you'll see the current will have a maximum value when that happens, okay? So if that's the case, then you solve for your frequency. Frequency is equal to 1 over 2 pi square root of LC, okay? So in this case, you will have maximum current. All that means you will have maximum response from the circuit, okay? So this frequency is called the resonance frequency of an RLC circuit, okay? So when you have that, then you have resonant frequency. And so then the resonant, the current, if you plot the current from the equation we give, we have about in the previous slides, okay? So IRMS is equal to VRMS divided by square root of R squared plus what, XL minus XC squared, okay? So then resonant frequency happens at this particular position, okay? If you have small resistance, then you have larger resonant current. If you have smaller, or if you have larger resistance, you have smaller resonant current, okay? And this is the mechanism of a radio device, okay? So the radio you have in your car or any standalone radio actually has a circuit, an RLC circuit in it, okay? So then you will tune your frequency by tuning or turning the diodes, okay? So then you can make your radio at a certain frequency, okay? If that frequency, that resonant frequency match up with the frequency from a radio station, all right? Then you receive the signal from radio station, okay? You get the maximum response, you get the maximum I, okay? So that picks up the signal. Otherwise, you get very small I that wouldn't give you clear signal, okay? All right, so let's take a look on the first example of the day on this, okay? So I'll give you guys just a couple minutes to have you get started on this one, and then we can look at the solution together, okay? Oops. All right, let's take a look on this one together here. So this one says to receive AM radio, you want an RLC circuit that can be made to resonant at any frequency between 500 and 1650 kilohertz. And to accomplish this, you have a fixed inductor of 1.00 microhenry connect to a variable capacitor. Okay, so what range of capacitance is needed? All right. So our resonance frequency F0 has a range from 500 kilohertz to 1650 kilohertz. All right. Now we know that for resonant frequency of an RLC circuit, okay, which basically is what you have in the radio, so it's equal to 2 pi square root of LC. Okay, so this is the equation we got in the previous slide. So then you are given fixed L, looking for the range of C. Okay, so you can see here, so you can replace this expression in the place of F0. Okay, then you'll be able to solve for the range of C. Okay, so basically this will tell you 500 kilohertz, then it's less or equal to 1 over 2 pi square root of LC, less or equal to 1650 kilohertz. Okay, so then we can look at this. So we can solve for this, okay, and then we can get a range of C. Okay, so if you multiply each side by 2 pi, okay, that will get rid of 2 pi here. So 2 pi multiplied by here, you put 2 pi here, you also put 2 pi here, okay, so then that get rid of 2 pi, all right, and then you can do the squares after that, okay, so each side you are going to square them, okay, so you're going to square each side, all right, so then you'll have here, you will have 4 pi square times 500 times 10 to the 3 hertz, okay, square less or equal to 1 over LC less or equal to 4 pi square, okay, so 2 pi, you need to square this, so it becomes 4 pi square, and then 1650 times 10 to the 3 hertz, okay, square, okay. Now this guy is given, all right, this is given as 1.00. So you're going to multiply each side by L, okay, so L here and then L here to get rid of L, okay. So after that, so this is 1 over C, all right, now you're going to do inverse of this, okay. So if you do inverse of this, let me just write this here. So 1.0 times 10 to the minus 6 Henry, that comes on, that's the L, okay, times 4 pi square times 500 times 10 to the 3 Henry, okay. If I'm going to do inverse to this one, okay, so then I got inverse of 1 over C inverse, okay, and then so when you do multiplication of a positive number, the sign here doesn't change, okay? But if you do inverse, then the sign here changes, okay? So less or equal to becomes greater or equal to, and then less or equal to becomes greater or equal to, okay? That's what happens when you do inverse. So 1.0 times 10 to the minus 6 Henry here, 4 pi square, 1650 times 10 to the 3 Henry, okay? The whole thing you are going to do the inverse, okay. Now this 1 over C, the inverse of that will give you just C, okay. So then this, if you place put the numbers in your calculator, this is going to be equal to 0.0101 farad, okay, and then on this side it's going to be equal to 9.3 times 10 to the minus 9 farad, okay. So then this is the range of your capacitor, the capacitance of your capacitor, okay. As this is the minimum, all right, this is the maximum, okay. All right, so yeah, so that's it for this one. Let me know if you have any questions, just unmute yourself and then ask me, okay. All right, so if not, then we'll move on here. So earlier I mentioned that the inductor doesn't consume any power in an AC circuit, and also a capacitor doesn't consume any power. The only element that consumes power is the resistor, okay? So then for an RLC circuit, this power in the circuit should be just coming from the power consumed by a resistor, okay? So for the resistor, it's going to be equal to I square, the root mean square quantity, times R, okay? Now for I, you can express in terms of V RMS divided by Z, okay? So then for the expression over here, so you have this, so you just write 1I in terms of V over RMS divided by Z, okay? So then here it becomes, the average power becomes VI, okay, or V RMS times I RMS times R over Z, all right? Now R over Z, we know that Z, let me write this on my paper here so you can also see. So we learned that Z is equal to square root of R squared plus XL minus XC squared, okay? So then R over Z should be equal to R over square root of R squared plus XL minus XC squared, okay? So you can imagine if you have a right angle triangle, okay? So if this is R, if this side is XL minus XC, or the other way around, whichever is bigger, okay, comes first. Then we will have positive number as that one, okay? So then for right angle triangle here, the hypotenuse should be equal to R squared plus XL minus XC square and then square root, right? So then if this is the angle phi, okay, so then cosine phi should be equal to R divided by this, okay? So we are using this notation like cosine phi. In turn, this is R over Z then, okay? Because Z is equal to that, okay? We are using writing R over Z as a cosine because that's what this right angle triangle represent, okay? And then this cosine, because cosine should be always have value of less than 1, okay? So then cosine phi here, it's called the power factor, okay? It's always less than 1, okay? So that means the actual power, the P average, is not equal to IRMS times VRMS, okay? But just a fraction of that by cosine of theta, of phi, okay? So this just indicates this average power is going to be less than that, okay? And then we call this as power factor, okay? All right. Now, the power factor can be also applied to not just an RL circuit, but it could be just an RL or RC circuit, okay? Not just an RLC circuit, but it could be in a circuit you only have resistor and inductor, and then it could be also in a circuit you have resistor and just a capacitor, okay? So let's take a look on the second example of the day here. All right, so this one says, determine the power factor of an RC circuit, okay? So in this case, we just have R and C, okay? We do not have the L, but you can just say XL then is 0, okay, in this case. So this one says, if R is equal to 4 kilo ohms, C is equal to 0.35, and so what will be the power factor here? Okay, when this is connected to a generator with an RMS voltage of 24 volts and 150 hertz, okay? So we are looking for the power factor, the cosine phi, which is in terms of R over Z, okay? We are given R, we need to figure out Z, okay? For an RC circuit, Z should be equal to square root of R squared plus, okay? For the XLC, then it's like XL minus XC square, okay? But we don't have L, so this simply is 0, okay? So just XC square minus XC square, it's the same as XC square, okay? So this is R square plus XC square, okay? So we just need to know what's XC? Okay, we can figure out XC by given the definition, from the definition. So 2 pi f times capacitance, all right? Here we know the frequency, we know the capacitance. So then we can solve for this guy, okay? So this, you just plug in the numbers, 1 over 2 pi, the frequency 150 hertz, okay? If you have anything in SI unit, then you can leave the units out. 0.35 times 10 to the minus 6 farad, okay? So it gives you 3.03 times 10 to the 3 ohms, okay? That's XC. Now you're going to put XC in here to figure out your Z, all right? So your Z then is equal to square root of, okay, 4.0 kilo, 4.0 times 10 to the 3 square plus 3.03 times 10 to the 3 square, okay? This gives you 5.0 times 10 to the 3 ohms, all right? So then you have Z here, you plug Z back in that one to solve your cosine of phi. Cosine of phi then equals to 4.0 times 10 to the 3 ohms divided by 5.0 times 10 to the 3 ohms, okay? Gives you 0.80 as the power factor, okay? All right, so you don't need to use the RMS voltage, okay, here, because you are just looking for power factor, okay? So that doesn't matter. All right. Any questions you might have? Just unmute yourself and then speak up, okay? All right, so if you don't have any questions, so let's move on here. So now, as I said, the power is only consumed by a resistor in an AC circuit, okay? So what happens if there's just L and C in the circuit? So called a LC circuit, okay? So then this is what happens, okay? You have a inductor here, you have a capacitor here, okay? So as a capacitor and an inductor, neither of them will consume any power. So initially, if you charge the capacitor, okay, then in the circuit, the energy here, after t equal to 0, the energy is going to be released from the capacitor, okay? So then it becomes current in the circuit, all right? Now, certain time later, you convert all the energy in terms of current. So then when a current going through a inductor, you have magnetic field, all right? So energy in the capacitor or in the electric field now is converted into the energy in the inductor in the magnetic field, all right? Now the magnetic inductor here is fully charged with the energy, fully stored energy here, fully converted in electric field. So then after that, now energy here is going to be released, okay? So then it becomes the charge on the capacitor again, okay? So if this is the case, then this process will go back and forth all the time, okay? So this is similar to, this is like energy transferring from one form to another form in form of electric field and then converted to energy in forms of magnetic field, and then other way around from energy from the magnetic field is being converted to the energy in the electric field, okay? So this is a resonance, okay, coming back and forth. Just like when in physics one, when we talk about a mass attached to a spring, if this is a smooth surface, so then if you pull the spring, the mass to one side of the spring, that means you are storing energy into the spring in terms of potential energy, okay? So if you release that, then the mass is going to go back and forth, okay? So potential energy converted into kinetic energy, and then kinetic energy convert into potential energy, back and forth, okay? So this is the resonance again, okay? So these two are analogs to each other, okay? So similarly, just energy stored in one form converted to another form, other form, and then coming back and forth, okay? So this is what happens when you just have a pure LC circuit, all right? So that will conclude the chapter 23. So then we'll be checking on 24 today, okay, chapter 24. So this chapter will not go into much details, but we'll just kind of skim through it, okay? So we'll just go quickly. It's basically kind of summary from what we learned in the electricity and then the magnetism, okay? So let's take a look here. This is on electromagnetic waves, okay? So it was like a couple hundreds years back that when Maxwell proposed that for electric field and magnetic field, okay? So so any waves, any visible light, okay? So he proposed that any visible light is actually an electromagnetic wave, okay? So like the sunlight comes to us and then when we see stuff, okay? So that's actually a form of electromagnetic waves, okay? And then he kind of proposed that we can use these four equations to describe any behavior of the electromagnetic wave, okay? Now, by saying that light is basically a EMF wave, so you can imagine. So when God created light, he probably says this language that we didn't quite understand, okay? So it's the differential equation and the calculus equation, okay? But fortunately, we don't have to understand that. We just need to enjoy it, okay? Okay, so yeah, so that might be what God says, okay, when he creates all this light stuff, okay? But anyway, in Maxwell's equation, okay, the four equations basically describe the behavior of electric field, magnetic field, okay, and then the energy stores in electric field, and then in magnetic field, and then the interaction of the charged particles with magnetic field, okay, and then the movement of the charges actually will create magnetic field, okay. So it's basically what we have been learning for the past months or so, okay. So on the electricity and magnetism. All right. So basically, if we don't have to use the calculus knowledge or differentiation equation, then this is what those equations says. It says for electric field lines, they originate on positive charge and then ends on negative charges. Okay, so we learn that. And then the first equation of Maxwell equation is basically from the Coulomb's law. Okay, that's just in differentiation form. Magnetic field line should be continuous according to the Maxwell equations, and then they don't have any beginning or ending. Okay, so they are in a closed loop. Okay, and then this is also description of Gauss's law for magnetism. Now, a changing magnetic field will induce a electric field, and then on the other hand, a changing electric field will induce a magnetic field. Okay, and magnetic fields are generated by moving charges or by changing electric field. Okay, so that's the fourth equation basically. So from Maxwell's equation, one can calculate that the speed of the magnetic waves is equal to 1 over square root of mu naught times epsilon naught, okay? Mu naught is 8.85 times 10 to the minus 12, and then epsilon naught is 8.85 times 10 to the minus 12. Mu naught is 4 pi times 10 to the minus 7, okay? So put those two constants into the calculation here, you will figure that the speed a magnetic wave is exactly equal to 3.00 times 10 to the 8th, okay? And then that's exactly the speed of light in vacuum, okay? So that also tells you the light is a form of electromagnetic wave. All right. So it was heard that actually came up with this device for the first time that you can actually receive a magnetic wave, okay? So basically, yeah, using an RLC circuit over here, okay, you kind of use that and in combination of a transformer over here, so then that will actually send out a radio wave or EMF wave, okay, and then you can construct a device, a tuner here. You can have this device to receive any EMF wave produced by this device over here, okay. All right, So that was the first when the magnetic wave was detected, okay, by the device. Now, to generate EMF wave, simply you can have two charges, or you can have like two particles that are charges, positive and negative. You can move them close to each other, all right, and then you can make them vibrate. Okay, so that means you can make the separation between them going bigger and smaller, going bigger and smaller. So you can increase the separation, then decrease the separation. So then there will be electric field generate. Okay, so the red lines here indicates the electric field. Okay, because electric field goes from positive to negative. Okay, so if that's the case, you can see if you are making this two charges moving back and forth, then you actually have varying electric field lines. Okay, so that means you have varying electric field. So if you have varying electric field, then you can have magnetic field generate. Okay, so magnetic field are represented by the blue here, blue cross, blue axis, and then blue dots. Okay, that indicates the direction of the magnetic field. So magnetic field should be going either into the screen or out of the screen in that way. All right. So that's simply what you can do to produce a EMF wave. Okay. So then after this, magnetic field is generated. Now magnetic field should be also changing, so then it will generate a second electric field in the red curve. Okay. In this case, it's not electric field. It's not generated by a charge. Okay, so the field lines looks like kind of different. Okay. All right. And then further on, if you have changing electric field, then you have changing magnetic field. Okay, so that just goes outward. Okay, that's how the EMF can be propagated. Okay. All right. So yeah, and then this is what you see. Okay, so the electric fields. Okay, so you can see if you make separation of the charges go up and down, or increase the separation going down in that way. Okay, so kind of oscillation. Okay, so you can see there's electric field going like this. Okay, so electric field will be changing as a sine function. Okay, so then you will generate a magnetic field also as a sine function in that fashion. All right. Now, if you look at the fields, so for EMF to propagate in space, so the magnetic field, all right, at any different locations, it's a sine function or cosine function. Electric field should be also a sine function or cosine function. All right. So they will be electric field and magnetic field will be perpendicular to each other. Okay, they will make an angle of degree, and then the propagation direction of the field, it's also going to be perpendicular to E and B. Okay, so then this is the case. This is the direction of propagation. This is the E field. This is the magnetic field. Okay. The strength of magnetic field at any location and then at any time t. So you can see the electric field as a function of location and also a function of time t. Okay, location of x and then also a time function of t. Similarly, magnetic field as a function of location and also function of time t. Right. So that's in a sine function. Okay, you see some people may write in cosine function, but doesn't matter. They are basically the same. All right. And at any time, according to Maxwell's equation, the E field is going to be equal to C times B, the magnetic field. So that means electric field strength is always going to be C times of the magnetic field. And C is the speed of light, 3 times 10 to the 8th. So 300 million times of B field. Okay. So that's always true. Okay. So if you are given E, then you can figure out B, okay, using this equation. All right. Now, this is the whole spectrum of EMF wave, okay? So only a very narrow part of it can be seen by our eyes, okay, human eyes. So that's this region over here. But basically, EMF covers the whole spectrum, okay? All right, so radio wave on the left, and then X-rays, gamma rays, whatever on the right, okay? Higher frequency, lower frequency on the left, okay? All right, the visible light are having a wavelengths are pretty much like from anything from 300 something to 700 something nanometers. Okay, that's the only part that we can see. All right. Okay, and so the X-ray can be generated, okay, by having an electron hitting on atom. Okay, so when that happens, the energy that the electron will hit another electron in the atom, so the other electron will be diverted in the direction over here. During the process, there will be energy lost, okay, which becomes the X-ray, okay, given out by the atom, okay. So that's how electron can be, or how an X-ray can be generated, okay. But we don't have to know the details, much of the details here in this class, okay. All right. And then this is just another picture showing how the X-ray is going to be generated. Okay. Now keep in mind this is just an imagination of what happens. Okay. What really happens inside atom is really complicated. Okay. We just come up with this theory and then that most likely describe it. But the real picture, I don't think anyone knows. Okay. All right, X-ray can be used to scan our body, okay, especially during this COVID-19 pandemic. This is being used a lot, okay, to see the image of the lungs. Now let's talk about the energy in an EMF wave, okay? So because an EMF wave is basically propagation of electric field and magnetic field, so then there's energy involved here, okay? So for energy, it's proportional to the field, so it's proportional to E field square and then also proportional to B field square, okay? So then we can check on the energy here. So in the electric field, the energy density is 1/2 epsilon 0 E squared. In the magnetic field is 1/2 mu naught B squared. Okay, so then the total energy in an EMF should be combination of the two. Okay, or the total energy density should be equal to the combination of the two. All right. And also given that E is equal to C times B, we can apply that all the time. And then C is equal to 1 over square root of epsilon 0 U 0. So the overall average energy density in an EMF could be either expressed just purely in terms of magnetic wave, magnetic field, or the B field, okay, in the RMS quantities, okay. So either this one or that one. All right. So if you just shoot a light on a board here, okay, so you can see there'll be energy delivered to the ball by the electromagnetic wave. Okay, so you can calculate what's the energy density there by doing the total energy divided by the area divided by time t. Okay, so let's call the intensity. Okay, so, and then by looking at this equation, we will realize that it's also equal to energy density times the speed of light, okay? And then I can be also expressed in terms of power divided by A, which power is delta U over delta T, okay? On here, this is the energy density, this is the volume, okay? And then divide by that, so that gives you that guy, okay? Energy density times the speed of light, okay? All right, so so then we have I equal to UC. All right, U average U can be expressed in terms of this and that, the electric field and magnetic field. Okay, so it could be also just purely expressed in terms of electric field and magnetic field. Okay, so in this case you can just use the so in this expression, this is the maximum E field, this is the maximum B field. Okay. All right. So on average, then it's equal to half of the maximum. Okay, so this is maximum density. Okay, I'll just have to go back one slide, but here we are looking for the average. So average will be 1/2 of that because E is a sign function, B is also a sign function. Okay, so I average energy density or the intensity, energy intensity here is equal to this expression here, or you can express in terms of magnetic field, okay, the maximum magnetic field there. All right, so there's two, either this one or that one, you can use either of them. All right, so I think that's how much we want to talk about EMF field. So at the end, let's take a look on this example here. This one says lasers can be constructed that produce an extremely high intensity EMF wave, electromagnetic wave, for a brief time, called pulse laser. Okay, so it's just coming in as a pulse. They are used to ignite nuclear fusion, for example. Such a laser may produce an electromagnetic wave with a maximum electric field strength of 1.00 times 10 to the 11 volts per meter for a time period of just 1 nanosecond. What's the maximum magnetic field strength in the wave? Okay, so in this example, we are just going to look at a few important equations here on EMF waves. Okay, so the first one is relating the magnetic field and electric field. Okay. All right. So as E field is always equal to C times the strength of magnetic field. Okay. So then magnetic field can be calculated by doing electric field divided by C. Okay. And then we are looking for maximum, so you can use the maximum magnetic field should be equal to maximum electric field divided by C. All right, we are given the maximum electric field. So 1.0 times 10 to the 11 volts per meter divided by C. This is a constant number, 3.8 times 10 to the 3.0 times 10 to the 8th. Okay, in meters per second. Okay, so this will tell us then the maximum magnetic field should be equal to 3.3 times 10 to the 2 Tesla. Okay. All right, so that's the one of the most important equations. Okay. Now, second one here, B is asking what's the intensity of the beam. All right. So the second one is looking for intensity. So you want to know equation for intensity of EMF wave. Okay. So and then it's asking the let me see the intensity of it. Okay. So intensity then equals to all right. So I equals to epsilon of C times epsilon 0, okay, times E squared, okay. So then if you are looking for intensity, I think it didn't put in the proper way. It could be like maximum intensity or average, okay. So let's just say we are looking for average. So for the average, so the maximum intensity then it's equal to maximum strength square. Okay, so then average should be just equal to 1/2 of that. So that's just assuming it's asking for max average. So then you are doing 1/2 3.0 times 10 to the 8. Okay, multiply by 8.85 times 10 to the minus 12. Multiply by the maximum strength of the E field, or positive 11 squared. Okay. So then that gives you 1.33 times 10 to the 19 watts per meter square. Okay, it's a very intensive laser. Okay. All right. The last we are looking for what energy does it deliver on a 1.00 area. Okay, so this is the intensity. So then you're looking for energy deliver. It's going to be equal to the intensity times the area times delta T. Okay. So then it's going to be equal to what we got there. Times the area is given as 1.00 millimeter square. So that means 10 to the minus 6 meters square. Okay, you want to do the conversion there. Now the time is given as 1 nanosecond. So times that time. Okay, it will tell you it's about 13.3 kilojoules. Okay, that much of energy is being given in that small area. Okay, so these are just application of some of the equations on EMF work. Okay, again, as I said, we are just going quickly through this chapter, so we are not going into cover much details of this. Okay, all right, let me know if you have any questions on this one. Okay, so if not, then I think we are going to stop here for today. Okay, again, homework wise due on Monday, and then on Wednesday we'll have our exam. Okay, so if you guys have no questions, then I will see you guys on Monday. All right, bye.